So here is a common base gain stage topology. As the naming suggests, because it says common base, the base terminal is the only terminal that is not connected to input or output. So you can see that the input is connected to the emitter, and the output is taken from the collector side. Okay. Now, if I want to do the small signal analysis, because the first thing that we do for these kind of topologies is that we try to calculate the gain, right? So let's actually draw the small signal model the way we have it in the bottom. So you can see that. Well, before talking about that, actually, let's make something clear. So this VB here is really a bias voltage, right? So a bias voltage, it's a DC, and the symbol suggests the same thing. It's a battery, so like you can imagine that, let's say it is, for example, it could be, I don't know, 1 volts, right? Now, how about the Vin? We know that it could be a combination of a DC plus AC, right? For example, the DC could be 0.3, so that the difference between base and emitter would be 1 minus 0.3, so 0.7. So it's around the biasing that we like to have across our base emitter diode to have a proper operation. And then so 0.3 volts plus some small signal, right? So small signal. It could be like a sinusoidal with a magnitude of 1 millivolts or something smaller than that, or a little bit large, slightly larger than that. Now, since VB is actually a DC voltage, when it comes to small signal analysis, it is an AC ground. That's why we connect the base side to ground. As for the emitter, it is connected to Vin, so I connect the emitter to Vin. And as on the collector side, I have RC going to VCC, and here I have RC going to ground, because VCC again is a DC voltage. In the AC analysis, it is as good as ground. Okay, and such as always, I basically draw the small signal model of my transistor with the I replace my transistor with the pi model with an R pi here and a GM pi here. Okay, now that I have my small signal model, I'm ready to draw I'm ready to calculate the gain. Okay, so I'm gonna use the same approach that I did with common emitter. I'm gonna call this I out, and I'm gonna say that V out is equal to RC I out, and I know that I out is negative GM pi, so it's gonna be RC times negative GM pi. And now I have to somehow relate V pi to Vn. Before, with common emitter, I had V pi equal to Vn, of course without degeneration. But here I noticed that if I write KVL over this path, I can say that 0 minus V pi minus Vn is going to be equal to 0. Therefore, Vn is going to be equal to negative V pi. So here I can actually replace negative V pi with Vn. So I'm going to get RC, or I can replace V pi with negative Vn, negative GM times negative Vn. So it's going to be just GM RC times Vn. So this tells me that the gain for this stage is going to be just GM RC, which is very similar to what I had for common emitter, the voltage gain. By the way, this is V out over Vn, in case it's not clear. So the expression is the same. The only difference is that with common emitter, I had a negative. So common emitter, just a reminder, gain was negative GMRC. Okay, so here I have positive GMRC, so that's nice, and it could be actually intuitively explained. So like with common emitter, you were actually applying the input voltage on the base side. So when you were actually increasing the voltage at the base, you were increasing VBE, so you were increasing the current at the collector. But here, when you're actually since Vin is actually at the emitter side, when I'm increasing Vin, I'm decreasing VBE, so I'm decreasing this. So it makes sense intuitively that it has the opposite polarity. Okay. So we have a GMRC, and as it's written here down here, we have the same kind of trade-offs that we had with the common emitter amplifier. What do I mean by that? Well, since gain is, or common base gain is equal to GM RC, I know that GM is IC over VT. Oh, sorry. So it becomes IC RC over VT. And now you can see that if I want to increase gain, again, if I want to increase GM, what happens is that I have to increase power consumption, so I have to increase IC. So that's something that I don't like. And at the same time, if I increase IC, even if I'm okay with the increase in the power consumption, when IC RC increases, it means that the voltage across this resistor is increasing, and that means that I'm pushing my transistor or my circuit more and more toward saturation, right? Which is something that I don't like. Why is it pushing it towards saturation? Because, well, the emitter voltage is constant, I'm not touching it, but I'm making collector voltage smaller and smaller and smaller, so the difference between the two is becoming less and less, okay? The other thing that I can see is that, okay, if I don't want to actually increase GM, if I don't want to increase gain using GM, and I want to do it using RC, then I don't have the penalty of extra power, which is good. But again, IC/RC increases, so I'm going to have a headroom problem, meaning that like I'm going to push my transistor to saturation again. Also, another bad thing is that, as we will see in a couple of slides from now, the output resistance of the circuit depends on RC, and if I have to increase the RC to get higher gain, I'm at the same time increasing output resistance of my amplifier, which we have discussed this before. It's something that we definitely don't like, because our amplifier on the output side is supposed to work like a voltage source. Therefore, ideally, it is supposed to have a zero output impedance.